Hello, everyone. This lesson will be a brief introduction to logarithms. To get us started, let's go ahead and take a look back at some of the information we talked about the last time we were together. We were studying exponential functions, and we looked at a lot of information. We looked at the graphs, we looked at some simple transformations, we looked at the connection to geometric sequences. But for this lesson here, it's important for us to remember that for a given base, the inputs of our expression represent the exponents, and the output of our expressions represent the powers. And we can see everything we need right here in this little expression. For some base, inputs are exponents, and the output represents a power of that base. Let's go ahead and work through a few power facts. So in the same way that we're going to be thinking of for a given base, whatever we place in this position as our input represents an exponent, and the powers that come out will represent our outputs. So let's start working in base 2. And we'll just go ahead and throw down a few facts involving base 2. For instance, 2 to the 4th power is 16. 2 to the 5th power is 32. 2 to the 1/2 power is the square root of 2. And 2 to the negative 3rd power would be 1/8. Now we can represent this information in a table where in the same way that the inputs represent the exponents, 4, 5, 1/2, and negative 3, and the outputs in the first column would represent the powers of 2 that correspond with those exponents. Now, what's not visible in the table is the base that's connecting these facts. And so one of the things we'll be keeping our eye on as we develop the concept of a logarithm and working with numbers in tables is what is the base that's connecting these. And if we think about our facts, we can recognize that the base must be 2 when we understand that these represent the exponents of that base, and these represent the powers of that base. Let's go ahead and look at this a little bit more deeply. I'm going to go ahead and give you an example of a table, and I want you to come up with the base that connects them. So right now you can see we have some input values, and we'll go ahead and say the same thing we've been saying, that these represent the exponents of some expression. Right now there isn't enough information to figure out what the base would be, but if I go ahead and give you some of the powers associated with that, for instance, let's say I provide for 2, 25, for 3, 125, for half, the square root of 5, and for negative 1, 1/5, the question is, what is the base? And if we know the base, then we can start writing the power facts that connect these exponents with those powers. I'm going to give you just a moment to look over this table, to reflect back on the previous one if you need to, and to answer the question, what is the base? Did you recognize that the base is 5 and that we can connect each of these rows to a fact? For instance, 5 to the 2nd power is 25. 5 to the 3rd power is 125. 5 to the 1/2 power is the square root of 5. And 5 to the negative 1 equals 1/5. All right, we're just about ready to introduce the idea of a logarithm. So let's look back on those 2 examples that we've used so far. And in both of these cases, we have just the inputs and the outputs. Those would be exponents and the powers associated with those exponents. But in both situations, the base is not clearly presented. we have a way, once we recognize what the base is, of writing these things in the form of our exponents as our x values, and our y values can be expressed in terms of the base by setting up an expression for the equation. Take a moment based on what we did with the last example and think about what the headers for these two columns will look like in example 2. Did you label this as x? And what would the y values be equal to? Did you write 5 to the x? If you did, then you're right. Now, one of the things that we're going to want to be able to do is to take sets of information like this and imagine what would happen if the powers were the inputs, and then the question were, what are the exponents associated with those powers? So let's just go ahead and take the same tables above and interchange the roles of the power and the exponent as input and output. So we'll list all of our powers from the table above here on the left-hand column. And on the right-hand column, we'll go ahead and put the exponents that associate with those powers relative to the same base. Now, it's still not apparent what the base is in this problem, but if we're able to figure out the base by looking at the table in example 1 up above, we can of course use the same base. We just have to sort of think of it in the reverse order. You may remember that when we interchange the input and output columns, we're essentially setting up an inverse function. So go ahead for a moment using example 2 above, and let's fill in the powers and exponents of this table. So we can use the powers 125, radical 5, and 1/5 to complete this column. And the exponents that match with these are 2, and 3, and half, and -1. Now the question that's before us now is, not only do we need to be able to see the base in the relationships in the table, but we also want to know what would be the equation that links the inputs and the outputs. We could certainly take the work above and say now that the x values are 2 to the exponent of y, but we still want to answer the question, how do we write this expression in explicit format where the y value or output is isolated? So that's the question that lies before us right now. It's time to define a logarithm. So let's think about it this way. Suppose you have a whole host of numbers, some tiny numbers, some bigger numbers, some really tiny numbers, maybe we have some really big numbers, and we want to know in all of these cases how to find that same relationship to them. It turns out that all of the numbers listed here could be thought of in one family of power facts. All of these represent powers of 10. And so let's go ahead and set up a table where we are going to put those powers, these values themselves, and let's go ahead and insert not just these ones, but a few others as well to build as much of the pattern as possible. We've got 0.1, we have 1. You might be recognizing that these look a lot like the place values in our decimal system. That's not exactly a coincidence. And now let's go ahead and set up a column for the exponents. And our job now is to try and figure out, number 1, what's the base? And secondly, what are the exponents associated with those powers using that base? Now you may have already figured out We've mentioned it briefly before that these are all in the power of 10 family, so we can take 10 as our base. And it might be easiest to go ahead and jump into some of the easy ones. 10 is the power of 10 to the first, whereas 100 is 10 to the second. Similarly, 1,000 is 10 to the third, and 10,000 is 10 to the fourth. Do you remember what power of 10 equals 1? Maybe you remember that 10 to the 0 power is 1. And now even if the other ones aren't as immediately obvious to you, we can definitely see a progression in these exponents, and you can compare it with your facts to see that -1, -2, and -3 would also be the corresponding exponents. So let's answer the question, what is a logarithm? The simplest answer to this question, and maybe this will be the most important fact for you to walk away from this video with, is a logarithm is an exponent. A logarithm is an exponent. So if we take a table of values similar to the table we had before, we've got our x's, we've got our y's representing our outputs, and let's just use a few of the values that we had before. Then we may have that when 0.01 was our input, remember that represented our power of 10, that the corresponding exponent in base 10 was -2. And similarly, when x was 1, y was 0. If our power is 10, our exponent is 1, and if our power is 1,000, our exponent is 3. So to come back to the idea of the equation that describes these outputs in terms of those inputs, we can use the logarithm function as a way of describing. Remember that a logarithm is an exponent, and that means that the output of the logarithm is the exponent you get when you plug in the corresponding power relative to this base 10. So to turn these back into some facts, now that we've flipped the table, we have that the logarithm of 0.01 is -2, and the logarithm of 1 is 0. Sometimes I'll use a scripty L, so it's easier to tell that that's a letter L and not a 1 or an I. Sometimes I won't use parentheses, and it'll be understood that this is 10 is the input of the logarithm function, and the log of 10 is 1. And similarly, the log of 1,000 is 3. And what that gives us here is a set of facts that correspond to the table now that we've switched the roles so that the powers are in the left-hand column and the exponents are in the right-hand column. Next, I want you to compare these two tables. Look at what in the tables is similar, what in the tables is different. Do both of these tables seem to fall into our discussion of relating exponents and powers of a base? If you recognize that both of these fit into that same conversation, can you identify the base associated with each table of values? Pause if you need a moment, but I want you to think about the base that relates the values in the first column with the values in the second column. Like we've done on the previous slides, the input column for each table represents powers of a certain base, and the output column represents the exponents associated with those powers. It's clear that since the outputs are the same and the inputs are different, the only change between the two tables can be the bases. All of the numbers in the first table are powers of 10, but more importantly, 0.01 is the result of taking 10 to the negative second. 1 is the result of taking 10 to the 0. 10, if we take 10 and use 1 as its exponent, etc. And similarly, over in the second table, all of these input values are powers of 3. And we need to verify that the exponents match up. So 3 to the negative 2 should be 1/9. 3 to the 0 is 1, etc. Now, when it comes to writing the equation for these two tables, we need to differentiate them because of their different bases, even though both of them have the same idea of inputting a power and outputting an exponent. That is to say, both are instances of a logarithm based on the input, and the way we distinguish them is their logarithms with respect to different bases. The way we regard the base is with a small subscript drawn in this position right here. So if the first table is calculating the logarithms with respect to base 10, and the second is representing logarithms in base 3, then this is how we'll distinguish those two functions. You may notice that your calculator has a button for logarithm, and we have a common way of writing logarithms without any mention of a base that's always understood to be a base 10 log, sometimes referred to as a common log. Now, here's a few more power facts. And we're going to start to distinguish the way we present our facts. These ones, what we think of as our ordinary way, we will now refer to as facts in exponential form. You can think of this as corresponding to when the exponents were our inputs and the outputs were the powers. We want to also be able to rewrite each of these power facts in logarithmic form. To do this, we need to imagine the idea of reversing the tables so that now the powers are the inputs and the exponents are the outputs. Now, these problems are different from other ones we've seen because these 4 problems are not in the same base power family. In fact, each one has the same exponent, but they come from different families. For us, that would have been from different tables. So we can go ahead and imagine that when we're dealing in base 9, we would have a logarithm in base 9. And now instead of having 81 as an output, we would have 81 as our input. And in logarithmic form, the first power fact would be stated as the log base 9 of 81 equals 2. Notice the language. The logarithm base 9 of 81 equals 2. We can express the second power fact as the log base 10 of 100 equals 2. Remember that that could also be written without the base 10, understanding that anytime no base is written, we think of it as a base 10 log. The log of 100 equals 2. Similarly, this one could be the log of 121 in base 11 equals 2. And the last fact would be the log of 144 in base 12 equals 2. Notice how the bases distinguish these facts, and they're all equal to 2 in logarithmic form because they all represent the same exponent in exponential form. So now I'd like you to try these. Write each power fact in logarithmic form. If you need to pause or go back to the previous slide, please go ahead and do so now. Our answers for these ones would be the log, this is base 10, so I'm not going to bother to write it, of 10,000 equals 4. The second power fact, the log in base 2 of 64 is 6. For number 3, when our base is 8, the log of 1/8 would be -1. For number 4, the log, we're talking about a base of 25. Our power is our input, and our output is half. And for the last one, log, we're in base 6 of 1/216 is negative 3. And for that one, it's helpful to know that 216 is the result of multiplying 6 times 6 times 6. Now I'd like you to try these examples. Evaluate each logarithm. I'll do the first one with you, and then I'd like you to pause the video and work on the other ones. So the way we'll think about evaluating a logarithm is the logarithm is a function whose job is to output an exponent. We're looking for the exponent in base 2 that produces a power of 8. Another way to ask this question is to think of it in exponential form. In base 2, what is the exponent we would need to give us 8 as the output power? And I know that 2 to the third is 8, so the log of 8 is 3 in base 2. Now pause the video and work on the other ones as well. How did that go? Were you able to make your way through them? I'll jot down the answers. The log base 10 of 100 is 2 because 10 to the second power is 100. The log base 3 of 81 is 4 for the same reason. Base 3 to the exponent of 4 is 81. Now this is an interesting one. All I've done here is interchange the base and the power. So instead of thinking about 3 to the what power would be 81, I want to be thinking about 81 to what power would give us 3. The difference is instead of building up from a small base, we're breaking down from a large base. Did you expect that result? You might need to keep practicing some of those. There's also a nice pattern here between these two to keep in mind. And for number 5, whenever we have a base that's 3 and our argument or input is 1/9, we're going to be looking at something like negative 2.